আচ্ছা, আমরা তাহলে শুরু করছি। ভয়েস আসছে তো ক্লিয়ার? ঠিক আছে। আচ্ছা, স্লাইডটাকে শেয়ার করি। দেখা যাচ্ছে?
হ্যাঁ স্যার।
ওকে। So actually, there are some points to discuss regarding Fourier series. It is not yet completed, not yet covered fully. মানে ওই বলে না বাংলায়, শেষ হইয়াও হইতে না চাই ওরকম আর কি। So যাই হোক, anyway, so in the last class we actually introduced this Gibbs phenomenon in the last class, and you know that it was first observed and discovered by, though it is after the name of Gibbs, okay, but it was first observed actually this kind of nature what we have discussed. So this was first observed and or better to say discovered by Michelson, the American physicist Albert Michelson. Now it was it was found that when we want to actually reconstruct, it's a kind of a square wave, suppose, or a rectangular periodic wave, when we want to reconstruct. So what happens that basically what we do, we have to take the help of Fourier series. Okay, we keep on adding the different harmonics, that means different terms, we keep on adding like this. And but what we observe when we are trying to reconstruct this kind of periodic pulse or train of what is called the train of pulses or chain of pulses. A minute. So this kind of train of pulses or chain of pulses, when you want to reconstruct with these different types of continuous time varying sinusoids, which are harmonically related to each other. Now, what happens at the vicinity of the discontinuity, or you can say the near the discontinuity, this is discontinuity, this is discontinuity. There are different discontinuities. So if we just take one pulse, okay, so it is very much clear that near the discontinuity or at the vicinity of the discontinuity, there is an overshoot. There is an overshoot সমস্যা হচ্ছে স্লাইড শো এর মাঝখানে জয়েন করলে না বারবার ইন্টারাপশন হয়। কি বলছিলাম? Yes, there is an overshoot and there is an undershoot at the vicinity of this discontinuity. There is a discontinuity, so near the discontinuity or at the vicinity of the discontinuity, there is overshoot and undershoot. There is overshoot and undershoot. There is overshoot and undershoot. Okay, so overshoot, if we consider this thing, this side, so overshoot it as the left and undershoot is at the right. So if you consider this side, so overshoot is at the right, undershoot is at the left, something like that. And if we just follow this different term, because it is already written that this first reconstruction or approximation or synthesis, different terms people use, so was done by only one harmonic, that is the first harmonic or the fundamental. And before that, of course, there is a DC part, because it is, you can understand, it's an event signal and there is a DC part. Anyway, so this is done by this, and then the next harmonics is basically the third harmonic, that's n equals to 3. So here we have basically three terms added. That means here we have DC as well as the fundamental and the third harmonic. Then here in this reconstruction, we have added another term, that is the fifth harmonic. So up to this, I mean DC plus the first harmonic, then the third harmonic and the fifth harmonic. And similarly here, case of 19, n equals to 19, that means you are keep on adding all the odd terms up to n equals to 19. So 19th harmonic you have added up to that. So whatever resultant picture we are getting, that is depicted here in this picture. So last one. Now the point is that actually we, as I'm trying to mention, that independent of this this kind of addition, that number of terms you are basically adding, independent of this overshoot and undershoot remains, that I mentioned in the last class, 9% of this steady value. This is the steady value or the final value. Okay, this is steady value 1, suppose it is 0, suppose. So 9% of that it is no. So that means the overshoot goes. In the last class you already told that it is, if it is 1, then the overshoot, the peak of the overshoot or the amplitude of the overshoot is 1.09, and if it is 0, then the minimum point or the this undershoot value is basically minus 0.91. So if the steady value is 1, varies between 1 and 0. Now this is okay, this is we have already learned. Now actually this incident, you know, I've already mentioned in the last class that this incident actually confused Michelson. Okay, Michelson thought there was some mistake, I think construction wise or technically there was some mistake, basically some error or some kind of fault, better to say, within the analyzer he developed. So that is why it is giving some erroneous data. He thought it is some kind of error is associated, and that is coming due to the the instrument itself. And that is why Michelson asked his friend, who was also an US mathematical physicist. Okay, so the difference is Michelson was only the physicist, and Gibbs, his friend Josiah Gibbs, he was from the same country, but he was a mathematical physicist. So I mean, in very simple words, you can say his mathematical background was very strong of Gibbs. So that is why he took the help of his friend. And Gibbs, and I mentioned, he took considerable amount of almost 1 year, okay, just to analyze this thing, which seems very simple nowadays. Okay, it's quite obvious, these things are obvious, okay, but at those times it was not so simple to understand. Now Gibbs was the first person who gave the exact the explanation, the mathematical theory, the theory that was based on fully mathematics. That is why I mentioned at each and every step, whatever Gibbs says, whatever he actually Gibbs said, better to say, all were substantiated by the mathematical proofs of the mathematics. So that it is beyond doubt that whatever we have seen or we have been discussing, everything is correct. There is no problem in it. So that is why that explanation was basically mainly based on the mathematics. Okay, and he told that what Michelson actually observed is correct. There is no instrumental fault or something like that. So it is the data generating or the result generating is not erroneous. There is no error in that. So actually, in that theory, he also established mathematically that why this is 9%, the overshoot and the undershoot, the peak in this and in that, right, at the edge or the near the edge. Okay, so why it is 9% and all these things, all these stuffs he discussed. It's actually proved, better to say, not only theoretically discussed, mathematically proved. Okay. So, but again, the mathematical proofs are beyond the scope, so we are not going into that. We are interested in the results. And now, suppose, let me, introduce or discuss with start with the signal, which is already known to you. This signal is this one. That means what we have already seen in the previous slide. This is something like this. A train of pulses is something like this. Goes on in all directions. In both the directions, sorry, not all, both the directions. And suppose this is minus T1, this is plus T1, the steady value is 1, the highest value is 1, and this is 0. Suppose this is xt, we write it as xt, this is 1, this is 0. And suppose you take this as suppose t naught by 2, and you take this side as minus t naught by 2. So you've already encountered this several times. So it's basically a periodic square wave, or you can say train of pulses or chain of pulses, whatever name you give, that doesn't matter, same thing. And it basically extends from minus infinity to plus. So it actually extended in both the sides in time domain. And whose width of the pulse is just 2t, extending from minus t to plus t, and the period is t naught by t naught. Okay. So if we expand this, in Fourier series, that what is going to happen? How can I write? Xt is equals to summation k equals to minus infinity to plus infinity ak to the power j k omega naught t. We know that very well. Okay, this is the expansion, the synthesis equation. And particularly for this example, it is a general formula. Particularly for this example, what value of ak we have already found? Just tell me what expression, exact expression. You have already done it. So what value of ak we have found? Sine. What was there in the argument? Quickly. Divided by something. Just refer the previous slides. In one of the previous slides, we have already discussed this. We have already done this calculation. So from that slide, you just tell me what would be the argument.
K omega naught T1 by K pi.
Just a minute. K omega naught T1 divided by K pi. Okay. K pi. Okay. So K omega naught, this is T1. Okay. K omega naught T1 divided by pi. This is the actual form. Just after doing the integration, you just got this form of AK. Okay. You just got it. So now what you can write? Suppose, for example, let me consider. Suppose this T1. Suppose this T1. This consider, suppose T1 is let T1 equals to T naught by 4. Say I'm just taking a case, particular case. So that means what? T1 is T naught by 4 means what? T1 is T naught by 4 means actually T1 is equal to half of this T naught by 2. That means T naught by 2 is the half of the time period, and this is basically 1/4 of the time period. We can also say like that. Okay. Now, under this consideration, or for this case, what we can write? That AK would be equals to, now just look at here, it is omega naught T1. No. Now, what is omega naught T1? If we just replace it T1 by T naught by 4, so you just replace it here. You just replace it T naught by 4. Okay. And now you know that what is omega naught into T naught? It is omega naught into T naught is basically your 2 pi. Okay. So 2 pi. So that means it would be just pi by 2. Okay, so it will be pi by 2. So I can write sine k pi by 2 divided by k pi. I can write like this. Now we just think the argument of the sine is k pi by 2. That means for even values of k, that will be non-zero, of course. For even values of k, is k pi by 2. Even values of k, suppose k equals to 2. Suppose k equals to 2. So it will be just pi. K equals to 4. It will be just 2 pi, something like that. So if you take the even values of k, then of course this whole term will become 0. And if you take the odd values of k, suppose 1, then it will be pi by 2. 3 pi by 2, and so on and so forth. So it would be what? Either plus 1 or minus 1. This term, this numerator, sine k pi by 2. Okay, so that indicates that in the expansion that we are trying to expand it. So this xt in this form. So in this expansion, the fundamentals and the odd harmonics would be there. That means for odd values of k, that ak has a non-zero value. For even values of k, ak has a 0 value. That means ak doesn't, and ak's don't exist actually. Okay, so that means there is a DC term. So we have already seen that there is a DC value, DC term or DC value, whatever you say, and that is a naught. We write like this, and which is from here we can understand that it will be just 2t1, the width of the pulse divided by the time period, which is the t naught. We know that. And in this particular case, when t naught is equals to, again I'm saying wrong, it is t1 equals to t naught by 4. When t1 equals to t naught by 4, under this condition it would be reduced to t naught by half. So it will be half. A naught will be half. So in the Fourier series expansion, we can write like your expansion. That means xt. This xt that can be written like the first term is the DC term, which is half, and the second term will be the first odd order terms, first harmony, and obviously it's even signal, so cosine terms will be there. So it will be just 2 by it will be just when k equals to 2. So k equals to not 2. I'm sorry, k equals to 1. So it will be just pi. It will be just pi, and you have to just write like it will be sine cos omega naught t, and k equals to 1. It will be pi. It will be pi. By the way, it will be not pi, it will be rather 2 pi. The point is, it's a trigonometric expansion. Okay, in trigonometric expansion, you know that actually if it were a exponential expansion, then you know that a1 equals to a of minus 1, which would be equals to 1 by pi. So in trigonometric expansion, we have seen that in one side, it is a one-sided expansion, and except DC, other than DC, all the harmonics and all the frequency terms will actually, the amplitude gets doubled. So it will be 2 by pi, okay, in this expansion. And then it will be, then the next term would be, I think, 3. So 3 means actually 3 pi by 2. So 3 pi by 2 means actually it would be ওটা কত হবে? 3 pi by 2 হলে ওখানেও একটা মাইনাস হবে, তাই তো? মাইনাস, এটা হবে মাইনাস 2 3 pi cos 3 omega t plus dot and so on and so forth, like that. So here we are getting this odd harmonics, cosine odd harmonics terms, okay, along with a DC. So this is the expansion. We already know that in one form we have already done it, and this is another way to represent. It's a trigonometric representation actually. Now, so what is happening, that is for n equals to 1. So for suppose, again, you just go back to this slide. Again, suppose for the n equals to 1, this cosine terms of this first harmonic, n equals to, this is 3. Okay, so as I mentioned, there is a first and the third harmonic, obviously along with the DC. Okay, then again, the next term is 5. For this 5, there is the first, third, and the fifth term is there, and so on. So that means if you just follow, take this middle path, suppose, and if you just follow the nature, that means number of ripples, that means the number of this oscillations, ripples means the oscillations actually I'm trying to make. Actually, if you look at this flat portion of this pulse, or this flat portion of the pulse, because as a whole, this is a one complete cycle. So whether you take this flat portion having the value 1 or this flat portion having the value 0, any of the flat portion if you take, you just see the number of ripples. There is the ripples or the oscillations that is actually increasing. And in the last class, I have already shown that if you just count the number of oscillations within a period, that will basically indicate this number. The last term you have added, the last frequency component you have added. And now the point is, these ripples are actually, kind of decreasing in amplitude as you are basically adding more number of terms. Just to see the ripples, the amplitude of the ripples, or the less number of terms, when you have added less number of terms, and you just see the number of ripples is increasing, but the amplitude is actually decreasing in amplitude. And not only that, if you move from the point of discontinuity to this, so this is the point of discontinuity. If you move from the point of discontinuity to either this direction or either this direction, depending on which flat portion you are concerned with, so that amplitudes of the ripples are continuously decreasing. If you keep on adding more terms, suppose you have added, say roughly 79. Okay, 79th harmonic you have added. Okay, so then obviously you can understand that how small this ripple would look like. Almost as if there is no width within that. Almost goes to 0. It looks like such. It will look like in such a way. And another point is another point to note, this at the edge or at the vicinity of the discontinuity, the overshoot and undershoot is still there, which is 9% of it's the steady value. That is true. That is not changing. And the height of this overshoot or the height of this undershoot, that's the amplitude or the peak value, that is not going to change as such. It is independent of addition of the terms. These are the few points. Now, this whole thing, these things actually as a whole, you can say it is called the Gibbs phenomenon. Okay, so as I mentioned, if you add much more number of terms, suppose if you think in terms of the Michelson's that analyzer which he developed, I have already mentioned total 80, n equals to 80, up to 80 terms that analyzer can add. That is a limitation of that analyzer. So suppose you have added 79th harmonic. So what would happen? As I mentioned, that obviously that these ripples at the flat portions they will be so small, so small that it will be kind of invisible. I mean, as if that it seems like there is nothing, almost flat. It's so small in height. But this overshoot and the undershoot, that will be there. But the area under this overshoot and undershoot will also diminish. and almost reduced to zero. Almost reduced to zero. These are the points to remember or note. Okay, so as I've also mentioned that this kind of Gibbs phenomenon is not only applicable only in the case of Fourier synthesis. Okay, it is not like when you try to reconstruct this kind of a periodic square wave or rectangular wave or a train of pulses like that, then only at the vicinity or this kind of things actually occur. It's not like that. Actually, as I mentioned, it's a fact of life. Okay, in reality also there are several cases, different cases in applications. There are different applications where if you try to reconstruct something, okay, where there is a discontinuity, this kind of behavior, oscillatory behavior, actually manifested. And actually, this is a fallacy somehow, because when we try to approximate a discontinuous function by a continuous function, because on the very first day I'm just trying to hammer this point that we are trying to approximate a discontinuous function, because this is a discontinuous function, with the continuous functions, with a large number of continuous functions. But where there is a discontinuity, then something would happen, and that is the actually fallacy. That something means actually some deviation from the continuity, and that is why that in that case your Dirichlet actually defined a value at the point of discontinuity. He defined that value would be the middle of the average of the mean of this these two flat portions of, okay, so it is something like that. So he defined, and in this way he told that, okay, every time, let's look at here, every time it is basically passing to this middle point. If it is 1, it is 0, it's a half. So it is every time it is passing to that. So that is also irrespective of the addition of the terms. Every time it is passing to this. Now, if you define this value, actually this is not my definition, as I mentioned, it is a definition or the way Dirichlet define. So then it is okay. Then both the sides will be okay, value-wise. But anyway, actually discontinuities manifest itself. The discontinuity of the original signal. Please note, the original signal which you are trying to reconstruct, that is manifested in terms of this overshoot and undershoot. When actually we are trying to reconstruct that with the help of a sum of continuous signals. Okay, so in this reconstruction process, whenever you actually call for, whenever you refer to, whenever you will deal with any kind of reconstruction process, and if there is a discontinuity in that, this kind of phenomenon, like Gibbs phenomenon, is bound to happen. This kind of oscillatory nature, overshoot, undershoot, this kind of things is bound to happen. And that is true. That is not only true for this Fourier series, okay, the synthesis of Fourier series or whatever, it is true for everywhere in life. That is in the, as I mentioned in the last, probably I mentioned that, a digital filter, when you will design different types of digital filter, there also you will see experience. That is a practical experience, the application that you will see, actually, the application of the Gibbs phenomenon or Gibbs phenomenon like behavior, you will see there. So it is a very, very, very important thing. Okay, its importance you will understand when you basically encounter different types of filters, digital signal processing class. Anyway, so this is the point to discuss. And okay, this is another point. This is a very interesting thing. Just to see, actually, if any kind of periodic signal is given, whether it is suppose a parabolic kind of shape, okay, or suppose a triangular shape, rectangular pulse, we have done many times, okay, different types of functions, periodic functions having different nature of variation, okay, the variation, how the signal is varying with respect to time. So here what happens in sometimes without doing mathematics, okay, just by looking at the nature of the signal, you can say that how its coefficients, the coefficients, okay, in the Fourier series expansion, you know the coefficient. These coefficients, you know that basically the coefficients for the higher order terms actually diminishes. If you add on different higher order frequency terms, harmonics, so basically the coefficients actually diminishes. But how they diminishes? Whether they diminishes linearly or in a non-linear manner. If it's a non-linear manner, then how fast? Okay, so just by looking at the nature of the signal, you can say there is a trick. Actually, this is kind of a trick, and you know that is sometimes helpful when you will go for any kind of competitive exam or any kind of viva. There, you will not get any chance to do the mathematics. But just by looking at the nature of the signal, you can say that yes, it is known that the higher order terms, the amplitude of the higher order frequency terms decreases, diminishes, falls very rapidly. But how rapidly? How rapidly? Whether that's the variation is linear or non-linear. If it is non-linear, then what is the order of that non-linearity, etc., etc. So it is something like, it's a very simple thing, very simple tricks you can just add up in any MCQ, in any kind of competitive exam also you can expect. So hardly 1 mark or 2 marks will be assigned. Just look at here. Suppose you have this kind of parabolic nature. Now, when you have this kind of parabolic way, suppose the number of differentiation you have to do to come from the parabola to this impulse. What is the number of differentiation you have to do? Okay, suppose let me start from here. I think that would be better. Suppose if you have this kind of rectangular or square shaped pulses, better to say. This is as you can understand, the DC value is 0 as far as this picture is concerned. Anyways, that is the different thing. Now here, if you just see, look at, there is a discontinuity. There is a discontinuity. Now if you differentiate this, obviously you will get some impulses at these edges. Okay, where there is a falling edge, where there is a rising edge, and so on and so forth. You will get some discontinuities. Now the point is, that when there is a discontinuity, the discontinuity means at this edge there is a discontinuity. So if you differentiate the way we shown while we differentiate the unit step function to get a impulse function, so it is similar to that. So if you differentiate, I will get a impulse whose amplitude will be negative because it is falling. It's a falling edge. And whatever the step height will be, that will be actually the strength or the area of this impulse. Okay, and this is just a height. Okay, don't get confused with this infinity. And this is the rising edge. So at the rising edge, there will be another impulse. Okay, again the step height, the difference will be the area of this impulse. Okay, the strength of this impulse. And again, so that the arrow upward, the arrow downward, and negative side, it will be positive side. Again, like that. So at each and every falling and rising edge, you will get one impulse. So the number of times you have to differentiate to get this thing from this is one. First time differentiation, you will get this impulse. Done. So that means you can say, if you have this kind of signals, but when you will go for its Fourier series expansion, the coefficients will vary like 1 by n. That means n, you know what is that? N is a number. When n equals to 1 is the first harmonic. When n equals to 2, it is the second harmonic. When n equals to 3, it is the third harmonic. You know that. We have already done it. Now, what will be the power of n? N is in the denominator because it diminishes as the number of term, higher order term. That means when the order of the term increases, that means the frequency value increases, it actually indicates the frequency component, whether it's the first harmonic or second or third or fourth. So as the value of n increases, n always in the denominator indicates that actually the amplitude or the value of the coefficient decreases or diminishes. Now here in this case, because the number of differentiation required to get this pulses, the train of pulses 1 from this, then the power of this 1 by n would be 1. It would be 1. So look at it. It is 1. So, and we have already seen it. We have done a mathematical problem. We have already taken up, I think in the last class or the last probably. And so there we have seen that how that higher order terms diminishes. Okay, so 1 by 3, 1 by 5, and so on and so forth. So just a few minutes ago, we have already seen. We have already did in the trigonometric expansion. We have already seen 2 by pi, 2 by 3 pi, 2 by 5 pi, and look at this. This 1 by 3, 1 by 5, 1. What is this? This is nothing but the terms, higher order terms, indicates the frequency harmonic. And always that n comes in the denominator, but with the power 1. That means diminishes, but not so rapidly or very rapidly. Now let's go back to this signal. It's a kind of triangular pulse, a periodic wave. And if you know that if you differentiate it once, you will get back this signal. And if you again differentiate once, that means you will get back this. So finally, you can say that by doing differentiation twice, it's a 2-step differentiation kind of. So if you do that differentiation twice, so you differentiate first, you get this, and then differentiate again, you will get this. So from this to this, if you want to come from this kind of signal to this impulses, so the number of differentiation required is twice, 2. So that means that again, higher order terms will diminish, of course, that is 1 by n, but the power will be square of that, 1 by n square. 1 by n square. That means it decreases even faster. It's 1 by n square. It decreases even faster than with respect to this. Okay. So when we expand, its coefficients will decrease even faster. So that means you just see from here the conclusion, what you can draw, that if you deal with this signal, and you know, in practice, we have to always go for the truncated Fourier series. Somewhere we have to truncate, somewhere we have to stop, isn't it? So that means the number of terms we have to take in this case is more, because the coefficient decreases less rapidly than the coefficients here. So that means when we are synthesizing the triangular waveform, we can even work with the less number of terms because the coefficient decreases even faster than the coefficients for this. So we can deal with the less number of terms. Are you getting the point?
Yes, sir.
Okay. Then if you start with this kind of parabolic nature signal or having parabolic nature, so you know that if you differentiate it, it's non-linear. Okay, you will get a straight line, so which is linear. Then from that, this kind of discontinuous thing, and then from that, the impulses. So that means the number of times you have to differentiate to get this from this is thrice, 3. First, second, third. So that means if you expand this kind of parabolic wave, again, the coefficient will diminish, but how it will diminish? The number of differentiation required is 3. So that means it is 1 by n whole to the power 3 or 1 by n cube. So that means the coefficients for this diminishes even faster, even rapidly. That means the number of terms required to synthesize this signal is much, much lesser. So in practice, when you will deal with this kind of signal having this kind of nature, obviously you have to deal with less number of terms, because after a certain term, because the coefficient decreases so fast, I mean after a certain point, a certain term, a certain harmonic, you don't need to bother to consider them. Okay, so in general, if you have any kind of signal for which if you suppose in general you need to do k times differentiation to get this kind of train of impulses or periodic impulses, okay, and then in general you can say its coefficient fall 1 by n to the power k in this way. So it is in general. So always when this is it's a very good application also, because whenever you will deal with this kind of in your analysis in future, I'm talking. So it is not only important for your MCQ and for the time being or any kind of competitive exam, that is okay, or Viva post, it's okay. But whenever you will deal with any practical signals in future, if you go in the lab and do some kind of practical experimental work on R&D, any kind of signal, whenever you will deal with, just by looking into the signal, you can from instantly say how its coefficient will decrease. The nature of decrease, it will decrease, but how it will decrease, the nature of its decrease, you can say. And that will basically ease your job by large extent. Okay, so I think this is, and now we are switching to what is called the Fourier transform from Fourier series. So now before doing it, let me start with this signal again. Okay, let me just clear the screen. We are already familiar with this, so let me start with this. I think that will be easy for us to discuss. Okay, so suppose again, just go back to this picture. Oh, I mean, erase kore keno fellam. Okay, take one pass. It is minus T1 plus T1 T0 by 2 minus T0 by 2. It is 0 xt and dot 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 dot. It is a periodic signal. Please note first. It is a periodic signal. I've just drawn only one period or something like that. Okay, so it's a periodic square wave, as you know, and its Fourier expansion we already know that it can be expanded like your xt, which is summation of k equals to minus infinity to plus infinity ak e to the power j k omega naught t. You know that. And again, remember this thing, I'm again emphasizing that it is a synthesis equation. It's an equation to expand this periodic signal into its coefficient or into its harmonics, okay, whatever way you say. And always this exponent of the exponential should have a positive sign. Always the positive sign associated. Just remember this. But for the analysis equation, whenever you will multiply and integrate, okay, in time domain, then the exponent will be negative. Negative sign will be there in the exponent of the exponent. So you just remember this thing. Don't get messed or confused with this. Okay, so this is the point, and we have already seen that AK can be written like sine ki bolla jano ota k omega naught T1, I suppose. I think I'm right. And k pi denominator. So ঠিক লিখলাম তো, এটাই তো বলেছিলে?
হ্যাঁ স্যার।
Okay, so it is like that. Now what we are doing, just see. So after writing this, okay, let me erase this part. So what we are doing or trying to do is we're trying to multiply it by omega naught, this side, and then divide by omega naught. Fine, we can do it. Now here, actually, I can say this omega naught into k, this part. So omega naught. Why I'm doing it? Because in the argument there is a term k omega naught. So this k omega naught or omega naught into k, whatever you say, it just put this k omega naught equals to omega. You just put it. K omega naught equals to omega. Now what is going to happen here? That it will be sine your it will be omega T1 divided by omega. This is omega. Yes, omega, and there is a pi term, and you just take this pi with omega naught. So you just write omega naught divided by pi. And you just now just do one thing. You just এটাকে just multiply by 2, denote both numerator and denominator. And what is going to this 2 pi? 2 pi can be written omega naught into t naught. It can be written like this. And if you write like this, just to look at here, this is omega naught, this is omega naught, so omega naught cancels, and this can be written like, you just see this, here is a 2, please note it. So 2 sine omega t1 divided by omega into 1 by t naught. This can be written like this. And now if we multiply this t naught ak with t naught, take this t naught at this side, so it can be written like ak t naught, which is equals to 2 sine omega t1 divided by omega. Under the consideration that when omega equals to k omega naught, right? Now what we have actually done, if we just follow these few steps, from there you can understand that at least from this where we have assumed that k omega naught equals to omega, what is the meaning of that? What is the implication of that? The meaning is that we are basically trying to think of omega as a continuous variable. Because k omega naught, it's basically, what is k omega naught? K omega naught are basically some discrete frequency terms. When k equals to 1, it is omega naught, because k after all integer. When 2 omega naught, 3 omega naught, so on and so forth. But when we are considering this equals to omega, that means these values are so close that I can assume them as a continuous. EK diagram I'm referring. তোমরা সেমিকন্ডাক্টর ইয়ে পড়ছো না, ফিজিক্যাল এন্ড ম্যাটেরিয়াল কি একটা আছে না, ইলেকট্রনিক্স কি একটা পেপার আছে না তোমাদের, ফিজিক্যাল ইলেকট্রনিক্স না কি এটা আছে না, এরকম একটা পেপার, ম্যাটেরিয়াল ইলেকট্রনিক্স কি একটা, ম্যাটেরিয়াল এন্ড ফিজিক্যাল ইলেকট্রনিক্স,
এটা অপশনাল, সবাই পড়ে না।
ও এটা অপশনাল, ও মাই গড, আচ্ছা আচ্ছা, এটা অপশন করে দিয়েছে এই বাবাই। আচ্ছা এই ইকে ডায়াগ্রাম তো তোমরা পড়ছো নিশ্চয়ই, বা জানো তো নাকি ইকে ডায়াগ্রাম? মানে জানো, ওকে, ভেরি গুড। সো ইকে ডায়াগ্রাম বেসিক্যালি তুমি যখন প্লট করো, বেসিক্যালি কিভাবে প্লট করো মনে পড়ছে? যে আমি ধরো একটা পার্টিকুলার কন্ডাকশন ব্যান্ডের রেসপেক্টিভলি আমরা এইভাবে প্লট করি। তো এটা মনে করো আমাদের ইয়ে কে, এটা মনে করো আমাদের ই, ঠিক আছে? ফর এক্সাম্পল মোমেন্টাম plot, momentum energy and momentum plot. Now actually this is not continuous. Actually if you have done the mathematics, you can understand my point that it is not a continuous thing. There are basically some discrete states, dot 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 dot. That means we actually draw like this. It's like this in both the way, and these dots state for an electron. Okay, state when the two consecutive states are very close to each other, very close in energy scale, very close, so close that it seems to be continuous. Please note the point. This is discrete. This is discrete. This is two discrete points, but two discrete points when placed so close to each other, it seems like a continuous. It is exactly same thing I am trying to bring here. Same thing I am trying to discuss in this context. These are the discrete lines, frequency lines actually corresponding to the frequency component, but they are so closely spaced. Now suppose you think of like this, that I can assume, that is why I ask you to put this, so that means it is kind of a continuous. That means here what we are trying to say, we are trying to think omega as a continuous variable. And this function, this sine omega t1 by 2 sine omega t1 divided by omega actually represents this. Now look at it. This actually represents the envelope. This actually represents the envelope. Envelope of what? Envelope of this thing. Ak into t naught. Please note, Ak into t naught. And you know what is Ak? Ak is simply the coefficients. And these coefficients, that actually corresponds to each of the frequency components or coefficients associated with each of the frequency component. You can also say like that. This is the point. And another point to note, you just see, suppose if your T1 is fixed, please note it. T1, what is T1? Look at this picture. Width. What is T1? T1 is the width. If your T1 is fixed, then this side is always fixed. This envelope is always fixed. And if you vary the T0 even, then this is at this side is fixed. So that means this product is also fixed. AK into T0. That means when you vary the T0, what is going to happen? Look at this expression. If you vary the T0, that means if you change the period, if you change, it's a periodic signal. If you change the period, keeping the width of the pulse same, then what is going to happen? If you change the period, then obviously the AKs will be impacted. Getting the point? Because it is 1 by T0 is there. Now, if you multiply this here and combine a term like this, then obviously the product will remain constant, because at this side there is nothing to go, no terms is going to change, and T1 is because T1 is fixed. So the envelope that we will construct will be independent of T0. That means if T0 changes, AK will changes, but such a way that the product will remain constant unless and until T1 is not going to change. This is the point I want to emphasize. Now, just if you draw it, let's suppose for example, select suppose for example, let me draw a picture. Suppose this is omega. Now we are writing omega in terms of omega, so it is omega. And as I mentioned, this is an envelope. And please note another thing. What is the peak value or the maximum value of this envelope? This sine 2 sine omega T1 by omega. What will be the maximum value? Which should occur at 0 when omega goes to 0. What will be that? You know that, right? I mean, it is a DC value after all, and the DC value would be this width 2T1 divided by the period T0 divided by the period. Now the period actually goes this side, so that means it will be only 2T1. Okay, 2T1. And then other components for both the sides, whether it's a positive or negative, doesn't matter, will fall. I'm drawing an arbitrary picture, specific value I am not considering. It will fall like this. Suppose in the first lobe I'm drawing, but first null I'm drawing. Completely arbitrary picture I'm drawing. Okay, I'm not considering any value. And suppose then it will basically reverse. There will be reversal. This spacing will be equal. Please note that. My picture is not so good, as always. কটা আঁকলাম 1 এই দুটো এই দুটো ওকে ঠিক আছে আর আঁকছি না ওকে এই অবধি থাক এরপর এটা কন্টিনিউ হবে so it will now if we connect the tips, if we connect or join the tips, it would look like this kind of sinc function, okay, damped sinusoid. So if you just connect these tips, Okay, it will look like this, and in this way it will basically go on at both the sides. Fine. Now, if you just see that, now let me mark a few points. This is 0. At 0, it is 2t1. Sorry. So, this the first after 0, when after DC value, the first component, the first line here I have drawn actually corresponding to omega naught, which is the fundamental frequency omega naught, that is the first harmonic or the fundamental itself. Then obvious that this side it will be minus omega naught. Then the second line means just ignoring this DC value without considering the DC value. DC value is always there, but if we don't consider this at the point, so that means that in this respect second. So it will be, or the second, the frequency component, you can say the harmonic, because DC is a 0 frequency component. So here we can say it is 2 omega naught, and then this side will be minus 2 omega naught. And the third one, so again, this is the third one will be 3 omega naught, and this will be minus 3 omega naught, and so on and so forth. In this way it will go on. Now we just see the difference between two consecutive, please note, the difference between two consecutive lines of the frequency component is what? 2 omega naught minus omega naught is omega naught. 3 omega naught minus 2 omega naught, omega naught. So in general, I can write, in general, in this way or that way, whatever way you go, you can write, if one is the k to omega naught component and its immediate successive components is k plus 1, then I can write k plus 1 omega naught minus k omega naught. Okay, in this plot, if you see in general, this is the interval, this is the difference in frequency scale, or interval, or the distance, whatever you say, between two successive lines, or two successive frequency components. Is this in general, which is nothing but omega naught, which is nothing but omega naught. And the first time it is crossing the zero, it is crossing. You know this argument, omega t1. Now, omega t1, the first 0 will occur when this will be equals to pi. That means what? That means the axis is omega, please note. That means when omega equals to pi by t1. So this point is pi by t1. Remember all these things. I need it. Pi by t1. So naturally this point will be minus pi by t1. Then the second 0 crossing point will be when it will be 2 pi. When it will be 2 pi means omega equals to 2 pi by t1. So it will be, this point will be 2 pi by t1, and this point will be minus 2 pi by t1, something like that, and so on and so forth. Okay, so we got the difference between two successive frequency components or two successive lines, because after all it's a line plotting. We know that line plot, and this and the 0 crossing points we have already marked, and we have seen that this envelope, that this continuous line is actually the envelope. Please note, actually they are discrete, but they're very closely spaced. Okay, but anyway, so we will see how close they are, and these things I'm just going to discuss within a few moments. But anyway, but this black line, don't get confused with this black line. This black line actually connecting the tips of these lines, and then it actually gives you the feelings of this function. So it is just an envelope in that sense. So this is a kind of this is a damped oscillation, kind of damped sinusoid. Sinusoids is being damped on both the sides as you are increasing the value of omega in both the directions, for the positive as well as for the negative values. So this is that thing. Fine. Sometimes this is not technically very popular, but in many literature you will find that this kind of plotting, it is, you already know that this is called the spectrum. It's a very popular technical name, spectrum, magnitude spectrum, phase spectrum, so on and so forth. Okay, and but sometimes people also call it a line plotting, line plot, whether it's one-sided or double-sided. Here it is double-sided, so it's a line plot. But sometimes loosely people also call it, like a it is a fencing. Fencing means it looks like a fence. Probably in the villages, you have already seen those have a flavor of that. That in the village, people actually erect their small houses or cottages with a fence made up of maybe bamboo or something like that. So it looks like a fence. Okay, so it is sometimes called the fence with a series of lines, or looks like a fence, so it is called the fencing. So this is not very popular, but again, in some of the literatures you also find this term also. Basically, the meaning is same. The sense is this. Okay. Anyway, so we keep the spectrum. Now, actually, this spectrum, this dashed, this lines actually, it corresponds to AK into T naught. Okay, this AK into T naught, these lines, all these lines, okay, all these vertical lines drawn by blue color, and this is not continuous. Please note it. The continuous lines, when we are joining the tips, and that looks like this envelope, which is governed by this expression or this mathematical expression or this function rather. Okay, now as I mentioned, this spectrum, whatever we have drawn, is magnitude spectrum as well as phase, both, which is single spectrum is good enough. Why? Because you know that when the magnitude is positive, phase is 0. So here you just see it is a positive number. It's a positive number. So there is no need to draw the phases. There is no need to draw. It is 0, means everywhere. And another point to note that this line spectrum, the difference between two successive lines in this line spectrum is omega naught. And the point is that suppose if I place these two consecutive lines in this line spectrum even closer to each other, that means what I'm doing, I am basically reducing this. The difference between these two, which is nothing but the omega naught, I am reducing in such a way that this k plus 1 into omega naught minus k omega naught seems to be almost equals to each other. That means the difference, this omega naught, can be written as del omega naught or d omega naught, better to say. Okay, so small, incremental change there is, very small, infinitesimal small. Are you getting the point? Then these two consecutive lines will be placed so close to each other, that means it seems like a continuous thing. Again, the third line I will place again very close to each other, close to the first two lines, like this. The fourth line I will place again close to the three lines, like this. The fifth line I will place again close to the already drawn 4 lines. So it looks like this. Now look at this spectrum. In this way, if you go on or move on in both the directions, so it will become a continuous kind of thing. Like the example or the analogy I cited in case of EK diagram. Okay. And this is actually the concept. In a very loosely I have mentioned or discussed. This is actually the concept when Fourier series converted to the Fourier transform. And why it is happening? What is the root cause? Root cause is this T naught. As t naught, if you change this t naught, as t naught goes to infinity, as you are increasing the value of t naught, the omega naught is keep on increasing. Decreasing. As omega naught is decreasing, the difference between the two consecutive lines in the line spectrum, in this fencing, so close that it seems like a continuous. That means when you increase the period, your spectrum is kind of, okay, try to convert or reduce from a discrete nature to a continuous nature. From a discrete nature to a continuous. In theory or mathematically, you can say, if you make this t naught infinity, that means the pulse, if the next pulse occurs after infinite time in both the sides, at this side or that side, so the distance between two consecutive pulses, because there was a pulse like here, what I have done, I have taken this and actually like this, take it and move like this, take another pulse at this side, again move it like this. So in this way, basically I am trying to increase the distance between two consecutive pulses, which is nothing but increasing the period. So in this way, if we take this next pulse and place it at some infinite point, so that means the distance between two consecutive pulses will be infinity. That means the period will be infinity. So then within the range of window, within the range of interest, this is nothing but a periodic signal. Obviously, we will not look beyond the window. We have a range of interest always, which is called the window. So within that window, if we look through or see through, then whatever nature I can see, I will just consider that or analyze on that. So that seems nothing but a periodic thing. It may so happen that beyond this window, that outside that window, the signal repeats itself. That is different thing. I don't bother. Are you getting the point? So in this case, when this will happen, this line spectrum, this discrete spectrum could look like a continuous thing, continuous spectrum, kind of. And really, that is very interesting. So that is why I always say, see, people say that when we have a periodic signal, we have to go for the Fourier series. When we have a periodic signal, we have to go for the Fourier transform, something like that. But in general, actually, that is, there is a one single line you can draw. One single line. Actually, Fourier transform is a special case of Fourier series, you can say, and the Fourier series is also a special case of Fourier transform. So one is not isolated from the other. One is not totally, there is a linking. There is no secret behind the Fourier series. So Fourier series can be extended for Fourier transform. The only thing is the period is infinite. The signal repeats itself after an infinite time. That is the thing. Otherwise, the techniques, the philosophy, the mathematics are all same. All same. So you don't need to understand the Fourier series and Fourier transform completely different perspective, different angle, different way. No, there is no need. People say, but I'm not interested to say like that. Because one is actually related to the other. One comes from the other. One is linked with the other. So there is nothing sacred behind a particular Fourier series or something like that. So in this way, suppose, for example, in this case, I can show you another thing that suppose in the last slide what we have drawn here, if we take the period equals to t1 by 4, and if you take the period for, suppose here I'm writing t naught equals to t1 by sorry, just a minute, don't write like this. I think it will be t naught. And 4, it will be t1 t naught by 16. That means t naught equals to 16 t1. here T naught equals to 41. So if we draw the spectrum, the spectrum, if we draw omega under this condition, the two cases I am taking just to give a comparative understanding. So you know that how the envelope will look like. The envelope will look like something. Envelope will look something like this. Like this. This envelope is actually corresponding to what is called T naught into AK. Just now we have seen T naught into AK. This is suppose 0. Fine. These are the 2 points. And what is the zero crossing point under this condition? T naught equals to 41. If you put the value in the argument, what is the function? Function কি ছিল? আরেকবার একটু বলতে হবে। ফাংশনটা ছিল কি? লাস্ট টাইম আমরা কি পেলাম? T naught AK equals to 2 sin omega T1, তাই তো? Divided by omega. And it was for omega equals to K omega naught. It was like that. Now, under this condition, when T naught equals to 41, under this condition, if you just put the value here, that T1 equals to T naught by 4 or something like that, if you just put here, then can you tell me what will be the first zero crossing point? What will be the first zero crossing point?
Four pi by T naught.
In terms of omega naught, you just tell me.
Two omega naught.
2 omega naught. Very good. 2 omega naught. Here it will be minus 2 omega naught. Very good. It is like that. And this is 0. This is 2 omega naught. So of course, there will be only one line, which is omega naught. So 0 omega naught, 2 omega naught. 0 minus omega naught, minus 2 omega naught, and so on and so forth. In this way, it will go. Again, it will be 4 omega naught. So in between, there will be only one line like this, which is 3 omega naught, and this is 4 omega naught. Here also, this is minus 4 omega naught. So then in between, there will be one line. In this way, we can draw. See, if we have a specific condition, then we can draw the exact figure, exact line spectrum, and this continuous line is just to join it, only to get this kind of envelope. Similarly, under this condition, suppose if we are interested to draw again the same kind of picture, so what is going to happen? So first we have to understand when the first zero will occur. First zero will occur at what value of omega naught? Just tell me. The envelope is not going to change because the last slide we have already discussed that my T naught is changing. T naught is T1 is same. T1 is same. The width is not changing. We are not changing the width, but what we are doing, we are basically increasing the time period from here to here. We're increasing the time period. So time period is changing. So that means actually that envelope will be same, independent of T naught. So I can at least draw the envelope. Now you just tell me, you do the calculation and tell me while I am drawing it, the same envelope. Okay, the same envelope. This is again the envelope means T naught AK, envelope of this. Okay, so this is 2T1, this is 2T1. T1 is not changing, so this side and this side is also same. And you just tell me first zero, when does the first zero will occur? Under this condition.
8 omega naught.
8 omega naught. Very good. 8 omega naught. 8 omega naught. So similarly, it will be minus 8 omega naught. So this is 8 omega naught. Please note, this is 0. This is 0. This is 8 omega naught. So that means in between there will be omega naught, suppose omega naught, 2 omega naught, 3 omega naught, 4 omega naught, 5 omega naught, 6 omega naught, 7 omega naught, and 8 omega naught. It is 0. 0 crossing point. So that means I have to draw, this is omega naught, 1, 2 omega naught, 3 omega naught, 4 omega naught, 5 omega naught, 6 omega naught, 7 omega naught, this 8. Similarly, in here also I will draw. And again, when I will get the second 0, second
16
0,
omega naught.
16 omega naught, very good, 16 omega naught. So that means after 8 omega naught, suppose 8, then 9, 10, 11, 12, 13, 14, 15, and 16 0. In this way, you have to draw these lines. This fence, you have to construct your fence. Okay, you have to construct your fence in this way. And such that the envelope would look like this thing. Fine. Now these two, if you now just compare these two, as I mentioned, it's a relative comparison. It will be very much clear from here. What we have done in the time domain, we have a signal, the pulse. The width of the pulse we have not changed. Please note, the width of the pulse we have not changed. What we have done, we have just increased the distance between two consecutive pulses. That means actually we have changed the period. Simply speaking, we have changed the period. So when we are changing the period, how this is reflected in the spectrum? When we are changing the period, suppose here the period was small, which is only 4 times that width. Actually, not 4 times. Actually, it is twice the width, because the width was from minus T1 to T1, so that means 2 T1. Anyway, so it is 4 into T1, half of the width. And it is 16 times the half of the width. That is 8 times the width. So more period. Period is more higher in respect to this. And as a result, within the first lobe, as well as second lobe, as well as third lobe, and each and every lobe or null, the number of lines increases. Number of lines increases. Number of lines, each line corresponds to the frequency component. And in this way, if you keep on increasing, the terms, if you keep on increasing the T0 value, then if you take 32 T1, 64 T1, and so on and so forth, 1 to 8 into T1, ultimately we'll see at one point these lines will be so closely spaced when you will plot this kind of fencing or line spectrum. It will be so closely spaced that it will seem like a continuous thing. It will seem like a continuous thing. That is the point I am trying to discuss. This is extremely important. This point you have to understand physically before doing any mathematics. Mathematics is okay, but before doing this, you have to understand what is actually happening. A periodic function, we know we represent that periodic function. For any periodic function, we represent in terms of the Fourier series representation or expansion. Now we have an aperiodic function. The way we got the aperiodic from the periodic, we have just done what you have done. We have just extended its period, just increase the period. The next occurrence, suppose we have given a very high amount of delay. So that the next occurrence, it seems like coming after infinite time. So now the function looks like an aperiodic signal. Now this aperiodic signal, so Fourier series, actually we can take to a limit. What is the limit? Limit is this, that T0 tends to infinity, mathematically. That means period tends to infinity. That means next repetition occurs after infinite time. And that is actually reflected in the frequency domain, in the omega domain. It's like placing the components very close to each other, so close that it seems to be continuous. That is why the spectrum becomes a continuous spectrum. This is the first step to Fourier transform from Fourier series. So we can say that Fourier transform generally applies to, that is why I'm using the term generally. I'm very consciously, carefully using the term generally. Applies to the Fourier transform applies to the periodic function, and Fourier series applies to the periodic function. For a periodic function, it is better to go for Fourier series, and for an aperiodic function, it is better to go for Fourier transform. But it doesn't mean, again, please note, it doesn't mean that two things are, should be dealt with separately. There is no relation, there is no link, that kind of isolated thing. It is not like that. There is no secret behind a Fourier series or Fourier transform separately or individually. Actually, that is why in general it is called the Fourier analysis. Doesn't matter whether it is series or transform. Actually, philosophy is same, concept is same, mathematical operations are same. Oh, okay. The point is, only thing you can understand, you may argue at this point, sir, in case of Fourier series, it was a discrete spectrum. In case of Fourier transform, it's a continuous spectrum. So how the analysis, mathematical analysis means actually what I'm trying to say, because the way we have already dealt with the continuous time and discrete time signals. In case of continuous time, we have to go for the integration. In case of discrete time, we have to go for the summation. The same theory will be applicable. But mathematically, actually, we're adding. Integration is nothing but the addition. That is the point I'm trying to say. So obviously, while you will deal with the Fourier series, that is a discrete spectrum. So obviously, you have to go for the addition. We have to write the summation sign. And here it will be, of course, it will be an integration sign because it is becoming a continuous thing. So it will be an integration. That is okay, but mathematical concept is same, na? What you are doing is basically same. There also you are adding, here also you are adding. The same thing. Okay, so this is the first step or first point. Though this discussion we have made is not so, very, very systematic way. It is kind of in a very, very crude and rough sense. Okay, just from the theoretical perspective or taking kind of an example, we have illustrated what is Fourier transform, how Fourier transform is coming to the Fourier series, how they are linked with each other, kind of things. But anyway, we can go for, we can become a bit formal also. We can formally derive these things. There is no problem in it. Okay, let me do it like this, like for you. So তোমরা কি এটার ম্যাথমেটিক্যাল ডেরিভেশনটা জানো? তাহলে আর আমি করব না, মানে if you know it, then I don't need to work out the same thing in the class. তোমরা how to mathematically, the formally, how to come from Fourier transform from Fourier series.
না স্যার।
ও আচ্ছা, ঠিক আছে, তাহলে করতে হবে। আচ্ছা, তো তাহলে আমরা যেটা শিখলাম সেখানে আমি আরেকবার একটু নাটস্টেলে বলে দিই যে আমরা যেটা বুঝলাম যে that we can say that all the frequencies actually present when we go for the Fourier transform from the Fourier series, because this Fourier spectrum in case of Fourier transform will be a continuous spectrum. Okay, because T naught tends to infinity means omega naught tends to 0, and that means in between two consecutive lines the distance in the frequency scale is almost 0. That is it, technically it is represented like del omega naught, okay, like this. Technically it is represented like this, or you can say del omega, doesn't matter, actually omega naught আর বলার দরকার নেই, so it is del omega বলতে পারো, so it is very small, infinitesimally small, so the things look like a continuous. That means now in this case, in case of a Fourier transform, the spectrum we are getting there, this thing there, actually you have different components, or rather better to say all the frequency components. All the frequency means, suppose between 0 to 1 hertz or 1 kilohertz, that is all the frequency component. Between 1 kilohertz to 2 kilohertz, that are all the frequency component. between 2 kilohertz to 3 kilohertz, there are all the frequency components. I'm talking in general, okay? So there are all the frequency components and so on and so forth. But in the Fourier series, what we had, we don't have like that. We have omega naught. We have DC along with the DC, if DC is there. Along with the DC, we have omega naught. We have 2 omega naught. We have 3 omega naught. That means omega naught and fundamental and its harmonics. In between omega naught and 2 omega naught, there are no frequency component. In between 2 omega naught and 3 omega naught, there are no frequency components. Oh. But in case of Fourier transform spectrum, the spectrum associated with the Fourier transform, it is not like that. In between any two frequency components, what we can say? Ideally, there are infinite number of frequencies. In between any two frequency components, there are ideally infinite, and they are not harmonically related. Harmonically related components are there. Those who are not harmonically related, they are also there. But so all frequency components are there, actually. So that is why, in case of Fourier series, we get a discrete spectrum. In case of Fourier transform, we get a continuous spectrum. Right? And yeah, before we go for this formal, derivation or discussion, at a point, can you observe one particular point that it is just for your interest? I'm saying, I don't know whether AK sir has already told or not, but still, I'm just saying that when you have in the continuous time domain, I'm talking, because in what we have done so far, the continuous time domain Fourier series, and now we are discussing continuous time domain Fourier transform. And AK sir has already covered the discrete time domain Fourier series, the DTFS, and discrete time domain Fourier transform. He has already covered. So you have already some understanding regarding what happens if Fourier series are transformed in the discrete time domain. Now in the continuous time domain, we have suppose this kind of, suppose I'm an arbitrary example. It's a continuous time domain. You have this kind of, suppose, periodic function. And when we find out a spectrum using Fourier series, it's like a tool. It's like a mathematical tool, okay? Using that tool, what do we got? We got a spectrum, suppose, for example, which is suppose like this. So which is basically two things to note. Here it is in time domain and it's a continuous. In time domain, the signal is continuous and it is periodic. In the frequency domain, the spectrum is discrete and it is aperiodic. Spectrum doesn't repeat itself in the frequency domain. You have seen it. Now, suppose if it is a Fourier transform, so far we have discussed, from this discussion you can say, if it's a periodic signal, Fourier transform, and the spectrum from this discussion, it is not omega, it is basically, or you can say, sorry, omega you can say, because it is after all, this, no problem, omega, okay. So it is also omega. So omega, so what do we get? Suppose, for example, we are getting this kind of spectrum, continuous. So we cannot draw with this line. It is not a line spectrum no longer. It's a continuous spectrum. So it is an omega domain because it is a spectrum, omega domain. So there are all the frequency components are present, suppose, and the spectrum looks like a continuous function of omega, and it is aperiodic. Have you observed these 2 points? And if you compare these two features, okay, both, considering both Fourier series and transform, and if you make a one-to-one comparison with what happens, that is a Fourier series and Fourier transform in case of discrete time signals, can you relate something? Continuous time case, periodic function, aperiodic function, and their corresponding spectrum. Discrete time case, again you have a periodic function, aperiodic function in time domain, and their corresponding spectrum. So can you see any relation? Can you establish any relation just by observation, without going or without understanding much details, just by observation? Any relation, any link, any similarity, something like that? কারোর মাথায় স্ট্রাইক করেছে এই জিনিসটা? Anything like that? Just to see, this is a periodic thing in time domain. When you are getting the spectrum, it becomes discrete in the frequency domain. So if you have something periodic in one domain, now I am generalizing, you just compare, because you have already vast knowledge on discrete time domain Fourier series and Fourier transform. You are well aware of this. You have done it, I think, much before we have introduced our Fourier series and transformation for the continuous time domain. So you know that if one is periodic, one function, whether it is time or frequency doesn't matter, if it is periodic, then the other domain, in the other domain, okay, the signal will be discrete. If it is periodic, then in the other domain it will be discrete. If it is aperiodic, in the other domain the signal will be, because it is also a signal in the frequency domain, it is also a signal in the frequency, the signal will be continuous. If it is aperiodic, in the other domain the signal will be continuous. Now you think in different way. If in one domain the signal is continuous, if in one domain the signal is continuous, the other domain the signal will be aperiodic. Look at this. Here also it is true. Here also it is true. Now you just think, now the whatever I have told you, now you apply in case of your discrete time case, discrete time signal. In the discrete time case, what happens? Discrete time, in a discrete time, if you draw a signal, suppose it's a periodic signal, suppose it repeats itself, suppose, and so on and so forth. What kind of spectrum you get if you go for the DTFS? Can you remember? What kind of spectrum you get? Archana, what kind of spectrum we get? If a discrete time signal is periodic, এই আমি কি কানেক্টেড আছি? তোমরা শুনতে পাচ্ছ তো? হ্যালো,
হ্যাঁ স্যার।
ওকে, না একদম সাইলেন্ট, আমি কিছু হঠাৎ করে ভাবলাম কি হলো, আমার কানেকশন চলে গেল না। ডিটিএফএস এ বলো কবে করেছো তো? স্যার তো করিয়েছে। কিরকম স্পেকট্রাম পাই? ইফ দ্য সিগন্যাল ইজ পিরিয়ডিক, ডিসক্রিট পিরিয়ডিক, স্পেকট্রামটা নেচার কিরকম হয়? আরে এটা হতে পারে, এটা কেউ পাচ্ছ না, এটা হতে পারে। আজকে কতজন প্রেজেন্ট আছে? ধরো 21-22 জন প্রেজেন্ট আছে। 21-22 জনের মধ্যে কারোর কেউ জানো না, কারোর মনে পড়ছে না? এটা হতে পারে না, এটা ইম্পসিবল। Similarly, if you have a aperiodic signal in discrete time, how does the spectrum look like? And if you go for the Fourier transform, DTFT, then how the spectrum would look like? এক্ষুনি তো বললাম, if a signal is continuous in one domain, then in other domain you will get a signal which will be aperiodic. If a signal is periodic in one domain, the other domain, whatever signal you will get, it will be discrete. এবার বলো এই যে সিগন্যালটা DTFS এর জন্য it is periodic as well as discrete. So if it is periodic, then what is going to happen? Your spectrum will be what? If it is periodic, your spectrum will be discrete or continuous?
Discrete.
Discrete. The spectrum will be discrete. First point. And second point is, if it is discrete, দুটো করে ফ্যাক্টর আছে, লক্ষ্য করো, দুটো করে কোয়ালিফাইং ম্যাট্রিক্স আছে, মানে সরি কি বলে মেট্রিসেস অ্যাকচুয়ালি, ওকে, সো প্যারামিটারস আছে. সো হিয়ার if it is discrete, then it will be, if one domain it is discrete, when one domain it is periodic, the other domain it is discrete. And again, this domain actually manifests two things. It is periodic, it is discrete. So when it is periodic, then it will be discrete. And when it is discrete, then it will be কি হবে? পিরিয়ডিক হবে. তো ডিটিএফএস যখন করেছিলে তুমি স্পেকট্রামটা কি পেয়েছিলে? ডিসক্রিট পিরিয়ডিক. টাইম ডোমেনের সিগন্যালটাও ছিল ডিসক্রিট পিরিয়ডিক. ইটস স্পেকট্রাম ইন দ্য ফ্রিকোয়েন্সি ডোমেন ওয়াজ অলসো ডিসক্রিট এন্ড পিরিয়ডিক. তাই কি পাওনি? হ্যাঁ কি না?
হ্যাঁ স্যার।
তাহলে চুপ করেছিলে কেন এতক্ষণ সবাই? সেটাই তো জিজ্ঞেস করছি. Similarly, if it is a aperiodic signal, aperiodic সিগন্যালের ক্ষেত্রে ফুরিয়ার ট্রান্সফর্মের স্পেকট্রামটা কি পেয়েছিলে ডিসক্রিট টাইমে? aperiodic discrete টাইম হলে বলো, when it is discrete, আমার সঙ্গে সঙ্গে বলো, when it is discrete one domain, the other domain will get periodic. When it is discrete in one domain, the other domain will get periodic. ঠিক আছে? তাহলে আমার যখন ফুরিয়ার ট্রান্সফর্ম করেছিলে পিরিয়ডিক পেয়েছিলে কি পাওনি?
হ্যাঁ স্যার।
And if it is discrete, if it is discrete, it is periodic in other domain. And when it is aperiodic, একটা হচ্ছে ডিসক্রিট, অ্যাপিরিয়ডিক. মানে বেসিক্যালি দুটো পয়েন্ট, একটা হচ্ছে পিরিয়ডিক অ্যাপিরিয়ডিক, আর একটা হচ্ছে কন্টিনিউয়াস ডিসক্রিট. নাও আমরা প্রথমে বললাম when it is discrete, if it is discrete in one domain, the other domain it has to be periodic. Fine. Now তাহলে এটা গেলে একটা পয়েন্ট, একটা ম্যাট্রিক্স আমরা আলোচনা করলাম. সেকেন্ড কোয়ালিফাইং ম্যাট্রিক বা প্যারামিটার সেটা হচ্ছে it is aperiodic. Now when it is aperiodic, it will be, the spectrum will also be continuous. তাহলে তোমরা মনে করে দেখো, তো এবার রিকল করো যে এরকম সিগন্যালে যখন ডিটিএফটি করেছিলে তাহলে কি পেয়েছিলে ফুরিয়ার ট্রান্সফর্ম করে? এটা এরকম ধরনের স্পেকট্রাম পেয়েছিলে না? পিরিয়ডিক বাট কন্টিনিউয়াস, হ্যাঁ কি না? এন্ড এখানে পেয়েছিলে পিরিয়ডিক বাট ডিসক্রিট. এটা আরবিট্রারি আঁকছি, ঠিক আছে? এগুলো তো অ্যাকচুয়ালি না. এবার বুঝতে পারলে ম্যাপিংটা? এই ম্যাপ, if you know this mapping, it is true indeed. সবসময় মনে রাখবেন অ্যাকচুয়ালি রিলেশনটা হচ্ছে এরকম, এই যে একটা হচ্ছে পিরিয়ডিক যদি হয়, তার সঙ্গে হচ্ছে এটা ডিসক্রিট. এই ম্যাপিংটা তোমরা করো, আমি দুটো লিখে দিলাম, একটা পিরিয়ডিক অ্যাপিরিয়ডিক, কন্টিনিউয়াস ডিসক্রিট. ইউ জাস্ট টেক দিস অ্যাজ এ চার্ট, একটা টেবিল হিসেবে চার্ট হিসেবে নাও. এইভাবে আমি যেটা রাফ করলাম এটা অ্যাকচুয়ালি এটা. নাও ইউ জাস্ট ম্যাপ. Look, just by observing, this is best observation. This comes from the observation, and it is true, in fact, in all cases. So, in continuous time and discrete time, একটা হচ্ছে continuous, একটা discrete, একটা periodic, একটা aperiodic. Basically, there দুটোই ফ্যাক্টর আছে, দুটোই প্যারামিটার আছে. So, like here, it is periodic. So if it is periodic, then its spectrum will be discrete. Means other domain. Other domain এটা discrete হবে। তুমি এদিক থেকে ওইদিকে আসতে পারো, এদিক থেকে ওইদিকে যেতে পারো, same thing. It is also like duality. It is called like duality. Okay, it is also like duality. Now look at this. এটা যদি দেখো, তুমি যদি ওমেগা ডোমেন থেকে এই ডোমেনে আসো, look at it. This is continuous. This is continuous and periodic. So when it is periodic, it will be discrete. Look at this in time domain. এইভাবে যদি তুমি দেখো। And when it is periodic, it is discrete. And when it is continuous, it is aperiodic. দুটোই তো মিললো। এই ডোমেন থেকে এটার এখানে যা এই কন্টিনিউয়াস টাইমে ফুরিয়ার সিরিজ আর ডিসক্রিট টাইমে ফুরিয়ার ট্রান্সফর্ম বেসিক্যালি এক, ইফ ইউ ফলো দ্য রিভার্স পাথ। দেখতে পাচ্ছ অ্যানালজিটা, সিমিলারিটি বুঝতে পারছো? ইট ইজ এক্সট্রিমলি ইম্পর্টেন্ট থিং।
হ্যাঁ স্যার।
কখনো ভুলবে না যদি এটা মনে রাখতে পারো। It's just a duality principle. In one domain, if a signal is periodic, the other domain, it will be discrete. If it is periodic, it will be discrete. If it is aperiodic, it will be continuous. If it is periodic, it will be discrete. It is aperiodic, it will be continuous. আর যেখানে দুটো ফিচারই পাবে, যেমন এখানে পেলে ডিসক্রিট ডিটিএফএস এ পিরিয়ডিক বলে ডিসক্রিট পেলে, পিরিয়ডিক বলে ডিসক্রিট পেলে, আবার ডিসক্রিট বলে পিরিয়ডিক পেলে। ঠিক আছে, মানে এর সিগন্যালও যা যেরকম নেচার, স্পেকট্রামও সেরকম নেচার, ডিসক্রিট পিরিয়ডিক। ভেরি ভেরি ইন্টারেস্টিং। এগুলো একটু আমি এই কনটেক্সটে জাস্ট আমার হলো বলে বললাম। আমি এগুলো তোমরা জানতে না, মানে এই অবজারভেশনটা খেয়াল করোনি যখন ডিটিএফ ডিসক্রিট টাইমে পড়েছো, এই লিঙ্কিংটা জানতে না?
অবজার্ভ করিনি অত ভালোভাবে।
অবজার্ভ করোনি, বাট এটা আমি যেটা বললাম এবার বুঝেছো সবাই? এভরিওয়ান ইজ ক্লিয়ার? এইবারে যখন তুমি রিভিশন দেবে না, ডিটিএফটি ডিটিএফএস কন্টিনিউয়াস টাইম, এইবারে ঠিক যেরকম ভাবে বললাম, আমি তো এটা খুব রাফ স্কেচ করলাম, এটা খুব একটা ভালো হয়নি আমার স্লাইড, মানে জাস্ট বোঝানোর জন্য তোমাদের বলেছি। সো অ্যাকচুয়ালি এরকম স্পেসিফিক সিগন্যাল নেবে যেগুলো তোমাদের এক্সাম্পল স্বরূপ আমরা করাচ্ছি বা বইতে করা আছে, সেরকম নেবে এবং সেখানে করে একটা নিজেরা চার্ট বানিয়ে রাখবে, টেবিল। এটা ইট ইজ লাইক এ ভেরি ভেরি হেল্পফুল টুল। এটা যদি মনে রাখো, জীবনে কোনোদিন ফুরিয়ার ট্রান্সফর্ম ফুরিয়ার সিরিজ ভুল হবে। ঠিক আছে, ইটস ভেরি ইম্পর্টেন্ট। ইটস কল্ড দ্য ডুয়ালিটি প্রিন্সিপাল। It is extremely powerful or helpful tool. যাই হোক, আমাদের আমরা কি করতে চাইছিলাম? একটা ফর্মাল ডেফিনিশন। সো ফর্মাল ডেফিনিশন আমরা করবো, তাই তো? একটা ফর্মাল ডিসকাশন করতে হবে। আমরা বললে ওটা তোমরা জানো না বলছো। তো ধরো, তো তার জন্য একটা আরবিট্রারি সিগন্যাল নাও। লেটস টেক অ্যান আরবিট্রারি সিগন্যাল। সাপোজ it is something like this. T1 to minus T1 to T1. It is 0. It is x of t. Okay. Say the height is 1. It is a triangular, okay, pulse. And we actually, what we are trying to do here, we want to go for a formal discussion regarding what so far we have done is kind of bit informal, bit superficial. Okay, taking a particular example or particular case, it's something like that. So it's okay in a in a lighter sense, it is okay. We have developed some understanding. Now here we have to prove it mathematically, kind of. So suppose it is an xt is a simple like a single triangular. It's a pulse that exists from minus T1 to plus T1, and the height of the amplitude is suppose 1. Okay, this is the shape of the signal, just the aperiodic signal. Now what we are doing? We are actually, we actually want to repeat this signal, okay, in both the directions. Then for the positive values of time, negative values of time, we are taking this and we are forcing it to repeat. So when it will be repeated in both the directions for both the values of time, then the signal will look like this. ছোট করে আঁকছি, জায়গাটা comp. So it will become like a periodic signal. Here also the same thing. 0. The pulse we do the same, minus T1 to plus T1. And it will be T0 by 2. It will be minus T0 by 2. Okay, this is 1. It's like that. And this is T0. It is 0. It is T0 by 2. It is T0. And this is 1. And this is এটাকে কি বলবো x bar of t বলো ঠিক আছে it is xt, it is x bar t. So x bar t is basically a periodic function. A periodic triangular pulses, periodic triangular pulses এভাবে বলতে পারো. Okay, so this pulse, this is a periodic function. When it repeats, আমি কিন্তু এটা কোনো example হিসেবে নিচ্ছি না. Please note it. It is not an example. In the previous case, we took an example of a square pulse, and then from that we got a sync function in the spectrum. Okay, the frequency domain, something like that. That is a specific example. And there we didn't do any mathematics to prove. Here we will do the mathematics, but it is just an arbitrary case I'm taking, because at a picture you have to take any arbitrary picture. Otherwise, how will we discuss? So that is for that. No specific example in that sense. Don't get confused. So this is a triangular pulse. When this pulse repeats itself in both the directions or for both the values of time, it becomes periodic. And we know what mathematical operation to do, plus to do to get a periodic signal from an aperiodic signal. Now, you just note that from these two pictures, it is quite obvious that this x bar t, okay, this periodic function x bar t should tend to xt when this t0, please note, when this t0 tends to infinity. That means mathematically I can write that x bar t tends to xt when t0 tends to infinity. I can write like this. Now please note, as this is a periodic function, s bar t, so I can write the Fourier series expansion for this. It's a periodic function. Let's start from the periodic, because that is well known. So we are trying to establish Fourier transform for the Fourier series. So what you can write? We can write x bar t summation minus infinity to plus infinity ak e to the power jk omega naught t. This is like this, where this ak কি ছিল 1 by t naught integration over a period. Integration over a period means এখানে say judiciously we are taking minus t naught by 2 to plus t naught by 2. So this to this, then only one thing. This is just a smart approach actually. So you can take from here to here, then the approach will be not so smart. You will understand why. So how you are taking the limit, that also indicates how smart you are. Okay, so this is like this, and then it will be x bar t, this periodic function, e to the power, and it will be minus sign in the exponent jk omega naught t dt. It is like this. Now you just see, in between t naught by minus t naught by 2 to plus t naught by 2, you just see carefully. In between this limit, within this, whether you are taking this function or you are taking this function, they are basically identical, and that is clear from these two diagrams. Within this limit, whether you take x bar t or xt, it doesn't matter. Basically, this was there. Okay, so I can write, you just erase this bar. So that means I can write ak equals to 1 by t naught minus this xt of this. I can write like this. Now please note another thing. Now when we can write it like an xt within this, now you just see, actually your t1 is actually less than t naught by 2, because t naught by 2 is somewhere here. So t1 is less than that. So if you take the whole range, like at minus t naught by 2 to plus t naught by 2, this range of limit. So basically you can split it into 3 parts. So one part is from minus t naught by 2 to minus t1. Second part, which is of course 0. So there is no need to write it. The second part is the only non-zero part is the minus t1 to plus t1. And the third part is again will be 0 from t1 to plus t naught by 2. So there is no need to write. So actually it is effectively equals to t1 to minus t1 to plus t1. Effectively it is equals to this. And now if it is true within minus t1 to plus t1, because that within that range it is only non-zero, and for the rest of the values it is 0. So rest of the values means if you basically go on up to infinity at this side and also go on up to infinity at this side, then also there is no matter. That means it is kind of adding the zeros. You know, it is analogous to the zero padding or zero adding. You have already encountered this thing in few occasions. Zero adding or zero padding. So it is something like that. So instead of writing t1 minus t1 to t1, I can also write it like minus infinity to plus infinity, same thing, because only within this range you have this non-zero value. For the rest of the values it is 0. So I can write like this. So now look how ak becomes. AK becomes equals to 1 by t naught integration minus infinity to plus infinity xt e to the power j k omega naught t dt. Okay. And now what is AK? What is AK or what are AKs? AKs are basically the coefficient of Fourier series in the x, or better to say the coefficient in the Fourier series expansion of this function. It is just an arbitrary function, any periodic function. It is a coefficient in the Fourier series expansion. So let's define a function in the frequency capital X of omega, or sometimes people write it like a j omega also. Please note, in some literature people use X of omega, in some literature authors use X of j omega. So same thing, any notation you can use. In my slides and my notes, there are two types of notation I use. When I will share the slide, you can find that I think, oh, here also I use X of omega. Okay, no problem. Same thing. So whether you use X of omega or X of j omega, basically same thing. Anyway, so let me define a term which is X of omega equals to integration minus infinity to plus infinity X of t to the power minus j omega t dt. Let's define this. The term I am defining. Okay, this is I am defining. Now, here, if you just compare this, with this, the way we define this X of omega and what is the form of AK we have got after doing this analysis, small analysis. Now, if you just compare these two, then what we can write? We can write that AK is basically nothing but 1 by t naught is already there, 1 by t naught, and you just see as the definition and what is there. It can be written like, if we replace omega by k omega naught, if we replace omega by k omega naught, then this is nothing but this. So it is something like capital X of k omega naught. Got the point? K omega naught is actually replaced by omega. Omega is a, you just put as if minus infinity to plus infinity is a limit, and now you are basically holding this to point, keeping in mind that what you have to keep in mind, what operation I'm trying to do. Probably you can understand what the sense that let t naught, this t naught, actually let t naught tends to infinity, which implies omega naught tends to 0. This implies omega naught tends to 0. And now what we are doing here, X of k omega naught, here it is e to the power j k omega naught t into omega naught, where actually the summation sign was there. Now what we are trying to, as if we are holding this to extreme points of the summation sign, and we are stretching it kind of when such that it from summations it become integration. under the consideration that t naught tends to infinity. When t naught tends to infinity, omega naught tends to 0. That means if we call this k omega naught as a continuous variable omega, because when omega naught tends to 0, you can understand from the previous example that the line, the fanes we draw, the two consecutive lines in the fanes, okay, they come so close. Omega naught tends to 0 means that it's so close that it's kinds of k omega naught becomes a kind of continuous thing, which is represented like by omega. So it become a continuous variable. And then the difference between two consecutive lines, they're so closely spaced, as I mentioned, the difference is this one here, omega naught. That omega naught is basically a small increment, because from omega naught to omega naught, k omega naught, 2 to 3, 3 to 4, like that. So small increment. So the small increment is so small that we cannot even write this delta, capital delta, we cannot write. Then it will be measurable. It is so small, it is not measurable. So that means instead of writing capital del omega, we have to write it like you have to write your d or del omega, or rather not omega naught, no longer omega. I cannot write omega naught, it is omega. The difference is, this is so small. Under the consideration that when k omega naught basically equals to omega, this. So now summation loses its significance. So as if we are holding this to point and stretching it, and it become integration. So when it become integration, then you just replace this by omega, okay, and this by omega, j omega, and this by d omega. And so if you write this correctly, then it would be 1 by 2 pi integration minus infinity to plus infinity capital X of omega e to the power j omega t d omega, something like this. So summation actually loses its significance because we are basically summing up infinitesimal small quantities. So see, philosophically it's the same. As I mentioned, we are summing up, but the sign we cannot use this, we have to use this. Okay, we have to invoke calculus, the concept of calculus, because it is so small that we cannot measure, and then we have to introduce the concept of calculus. And but technique is same, mathematical philosophy is same, the understanding is same, okay, the analysis, the method of analysis is same, everything is same. But the just only thing is that the notation is changing, you are changing, fine. And this is d omega. D omega is this the small incremental change. This is so small that you cannot measure even that change. It is between, actually it was between two consecutive lines. Distance between two, or difference between two consecutive lines. Fine. Now you just think the story is not ended yet. The x bar t we have written. Now you just see when t naught, please note, when t naught, because we have already written t naught tends to infinity. When t naught tends to infinity, now you see then x bar t and xt. X bar t was a periodic function having this nature, and xt was an aperiodic function. But when this periodic function, when t naught tends to infinity, this point, then obviously this and this are identical, na? There is no difference. So the whole functional form I can write. So here there is no need to write x bar t. I can write xt, the same thing, because ultimately we are getting this under the consideration of this. Under the consideration, this and this become identical, equal to same for all the values of t. So that means the whole functional form at the left hand side, there is no need to write x bar t. You can write xt, which is nothing but this. So what you got actually this. Now if you just I just clear the screen and rewrite it again. X of t, x of t is 1 by 2 pi integration minus infinity to plus infinity capital X of omega e to the power j omega t d omega. That was form we have written. Now, so what we have done, or what understanding we can develop? So suppose we have a function xt, which is aperiodic. Its Fourier transform x of omega, capital X of omega, that can be written like the definition we made there, minus infinity to plus infinity. We have defined it like this: x of t e to the power minus j omega t dt. So this is given an aperiodic function xt. Its Fourier transform is a capital X of omega, and given the transform x of omega in the frequency domain to you can multiply by e to the power j omega t, integrate about all the values of frequency, and then divide by 2 pi. Whatever you are getting is the original signal, or rather trying to get back to the original signal. So the point is, obviously, as you can understand, this equation is the input, it's kind of input, it is the output. So xt is given, time domain signal is given, you are finding out the frequency domain spectrum. So it is kind of an analysis equation. It's analysis, and look at this, an analysis equation, as always, as in the previous case also, the exponent of the exponential have a negative sign. And this is the synthesis, because frequency domain is given, and with the help of that you are trying to construct or reconstruct or get back to the original time domain version. Okay, so but it is called kind of synthesis equation. Here, previously in the case of Fourier series, it was summation, now it is integration. And obviously you have this factor 1 by 2 pi. Now this synthesis equation, you just note you are multiplying, you are using exponential, complex exponential, but the exponent of the exponential has a plus sign, positive sign. Okay, so this is this analysis equation. This equation is actually represented, or better to say, actually defined. Okay, actually defined. This line you should use like a Fourier transform of x of t. Fourier transform of x of t. This is the analysis equation. Okay, and this is defined as the inverse Fourier transform of x of t. Okay, the inverse, which is a synthesis equation. Now please note that integration, in both the cases you have to do integration. You have to resort to the operation which is called integration. But in the Fourier series case, analysis equation was the integration, but the synthesis equation was the summation. But anyway, here in both the cases you have to do the linear integration. Integration is basically a linear operation. You know that. So we are operating xt, which is a function of independent variable time, and we are operating on that. Is xt. We are operating on that, and we are doing this linear operation, which is integration. And after this operation, we are getting, or we are going to another domain, that is the transform domain or the frequency domain, where we are getting another function, capital X of omega. Again, here the independent variable is omega. Please note, not time. So in doing this operation, actually what is changing? See, the time domain is converted to the frequency domain. The t is changing to the omega. That is the one point. That is independent variable is changing. Not only that, please look at the notation. Here I have used small x, here I have used capital X. That indicates the dependent variable. The dependent variable is also changing. So not only the independent variable is changing, but also the dependent variable is also changing. This is the point to note. So sometimes Fourier transform is called, it's a linear operation of transformation. Linear operation of transformation. That is one function, whether you see this or that, doesn't matter, same thing, same story. This is Fourier transform, this is the inverse Fourier transform. Okay, so because sometimes the question may ask whether if time domain to frequency domain journey is possible, you can go from this to this. Whether the reverse route is possible, whether the reverse journey is possible, that is frequency domain to time, it's also possible in a case of, like in the case of Fourier series. Okay, or for other types of transformations. say Laplace Z, etc. It is also possible. So whatever the thing is given, in whatever domain it is given, the signal. So when you do the transformation, whether the forward or the reverse, so basically you are not only changing the independent variable, you are also changing the dependent variable. Look at it, it's small, it is capital. Here also it is capital, it is small. These are the points to note. Fine. And another point to note that this scaling factor 2 pi, the scaling factor 2 pi, in case of the inverse Fourier transform, that is the synthesis equation concerned, this one, there is a scaling factor 1 by 2 pi. And in this context, I want to say, because though for them who already have an understanding of Fourier transform in the math class, or in the subject of mathematics, they have already encountered Fourier transform. There probably you can remember that there is no such, either there is no such multiplicative factor, or it was some other factor they use. Because the most of the books of mathematics, they use, either they don't use this factor or they use some other factor. But please, as an engineer, as an electrical engineer, we will not bother with this. We will only use, we will stick to this factor 1 by 2 pi, and you know how this comes. We have already derived. Okay, so you know the root from where it is coming. And that is extremely, extremely important. I'm saying, I'm again emphasizing this factor, this part, this fact. That 1 by 2 pi factor is not just a factor you whether consider or not, doesn't matter. No, you have to consider 1 by 2 pi factor. As an engineer and an engineering application, everywhere, whenever you will go, you have to take into account this, and based on that, all different properties, the value, their spectrum, everything will change if you don't consider this factor. Okay, so you have to consider this factor. So I am giving it a special emphasis. Okay, so so these two equations, as you know, as a again in the case of Fourier series analysis and the synthesis, this two is a complete statement of Fourier transform. Complete statement of Fourier transform. It's a complete information. These two together. Okay. So from time domain to frequency, frequency to time, so both side journey or direction or movement is possible, transformation is possible. And sometimes also, please note that I've already mentioned this term, it is called the transform domain. Mainly the frequency domain is called the transform domain. That generally signals are given in the time domain, because time domain we can sense, we can visualize. The frequency domain, it is difficult to visualize or sense or to perceive. But for the analysis purpose, it is better. It is good. That is why we transform it. So that is why people call it a transform domain. তোমরা যখন পরবর্তীকালে in the next course or probably in the higher courses, or even if you're interested in the research, if you go for dealing with the image processing, advanced image processing or something like that. In the image processing, if it's a still picture image, so there, at each and every point, the intensity of the color or some other information is actually varied from point to point in space. So obviously that will be spatial variation. So when you basically extract this, there will be variation with respect to space, not time. If it is a still picture. Now if it is a moving picture, you know that there will be the variation of space as well as time. So in general, you can say whether the variation is with respect to space or time or both, but it is multidimensional. Okay. So when you transform it, you can transform it to the frequency domain. And this frequency domain, and whatever tool, whatever method you use, whether the Fourier or Laplace or Z or any other kind of advanced versions or tools, if you use, or the algorithms even, if you use, and if you convert it to the frequency domain for the analysis, then that is called transform. But transform domain, a word that maneta hocche tomar oটাকে frequency তে নিয়ে যাওয়া যায়. Whether it is an image or any other signal or the speech or any other signal, or say both the variation with respect to time and space, it is converted to the frequency domain. It is called the transform domain. আর একটা পয়েন্ট হচ্ছে যে নোটেশনটা, the notation we use, that is the inverse. Please note, it is not any physical reciprocation. It is not 1 by inverse in that sense. It is just an operational notation. That the operation is what operation you are doing the inverse Fourier transform. That is, you are going from the transform domain to the time domain. So that is why this notation is used. It is not, the meaning is not just you take any value and just you reciprocate it. Okay, it is not like that. So sometimes students do it, that they, whatever frequency domain values are given, they just take and make a 1 by that. It is not like that. It is not like a resistance and conductance kind of thing. The resistance you have, just take the reciprocal of that, it become conductance. No, it is not like that. You just understand that. Okay, it is not a physical reciprocation. It is just an operation which we are trying to indicate with this symbol or with this notation. Fine. And another thing is that this is already mentioned in the here in the slide. It is already mentioned. These things we have already discussed. So the point is that as we can move from the time domain to the frequency domain and from the frequency domain to the time domain, both is possible. That the analysis equation, synthesis equation together, as I mentioned, it basically gives the complete information of the complete statement and information of the Fourier transform. So sometimes technically these two is called Fourier transform pair, FTP, Fourier transform pair. That means xt capital X of omega or xt, sometimes people use this sign also, capital X, either this or that you can use. So basically it indicates the both sided arrow indicate, that means you can go from this to this forward path or it's a reverse path. Both the sides is possible. Here also the same thing. Okay, it is alternative notation people use, the both sided arrow. So sometimes in the question paper we just mention this thing, this kind of notational approach. Sometimes the question statements use or take. This is just mentioned without writing in words or in sentence, without writing. They prefer to write like this. Xt, this is this. The meaning is that xt and x omega are the Fourier transform pair. But instead of writing this in language, that is xt and x omega are the Fourier transform pair, instead of writing that, they just prefer to use this or this. So the meaning you should understand that this is the meaning is the both side journey or the transformation is possible. You can go from this to that or from omega to time. But whatever you are doing, or whenever you are doing, you have to remember that not only the independent variable is changing, but also the dependent variable is changing also. But say the value is also changing. Dependent means the value is changing. The value is also changing. Then you have to understand this point. So both, either this or that, whatever notation you use, or it is used in the question paper. So you have to understand that this is the meaning is a transform pair. That means both the analysis and synthesis equations are involved here within this. Okay, ঠিক আছে, আজকের মতো থাক এই অবধি। আচ্ছা, আর একটা ক্লাস নিলেই হয়ে যাবে আমার ফুরিয়ার ট্রান্সফর্ম। আচ্ছা, সেই ক্লাসটা তাহলে আমরা কালকে নেব। ওকে, আগামীকাল মঙ্গলবার। কটা থেকে করবে বলো?
সকালেই করুন 10টা থেকে 12টা।
স্যার এই টাইমটা ঠিক আছে।
এই টাইমটা ঠিক আছে? আচ্ছা, এই টাইমটা ঠিক আছে। তাহলে কালকে 10টা থেকে 12টা। কালকে হচ্ছে 18 তারিখ। ওকে, 10টা থেকে 12টা। ঠিক আছে, তোমরাও নোট রেখো, আমিও তাহলে এটা একটু করে রাখছি। আচ্ছা, কোনো কোশ্চেন বা কোনো ইস্যুস আছে সোফার? থাকার কথা না, আজকে বেশি থিওরিটিক্যাল আলোচনাই করলাম, যদিও তোমরা এগুলো তো জানোই মোটামুটি, ম্যাথমেটিক্স পড়েছো। স্টিল জিজ্ঞেস করছি যদি থেকে থাকে।
না,
ঠিক আছে। আচ্ছা, অ্যাটেন্ডেন্সটা আমি একটু নিয়ে নিই। 303 roll 303 set 306 absent 307 নেই 8 present 308 বললে না?
Yes, sir.
308. Okay. 308. 309.
Present, sir.
310. 310. 11.
Present, sir.
13.
Present, sir.
15. नहीं 16.
Present, sir.
19. 321. 321. Absent. 322.
Present, sir.
24.
Yes, sir.
25.
Present, sir.
3 ইয়ার্স কেউ বাকি আছো? বাদ গেছো এরকম কেউ আছো? আচ্ছা 4 ইয়ার্স 401.
Present, sir.
6.
Present, sir.
8.
Present, sir.
11. 411. Absent. 416. Absent. 418. 9. 419. Absent. 420.
Present, sir.
425.
Present, sir.
427.
Present, sir.
428.
Present, sir.
9.
Present, sir.
30.
Present, sir.
1.
Present, sir.
2.
Present, sir.
3 4 तो नहीं 435. 435. Absent. 436.
Yes, sir.
37. 437. Absent. 438.
Present, sir.
4 ইয়ার্স এ কেউ বাদ গেলে কি আছো এরকম? নেই তাই তো? ঠিক আছে তাহলে কালকে 10টা থেকে। ওকে, থ্যাংক ইউ।